Warning! The video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. I speak to you in a very somber tone because this is the final video that you'll see of mine for differential calculus. I may have a video series for integral calculus. In fact, I do have some, but this is the final video in a series for differential calculus. It is all about evaluating integrals using a substitution rule. It is assumed that you know the substitution rule or have been exposed to it at this point. So let's go ahead and tackle very common substitution rule problems. And throughout this, I'm going to give you some tactics. All right, so let's go ahead and tackle this. Example, evaluate this indefinite integral. Now, do you happen to know what you would take the derivative of to arrive at that? That's the very first thing you should always ask yourself. What do you take the derivative of to arrive at the integrand? If you don't know, then that means you're probably going to use a special technique. An integration technique is what we'd call it. And the special integration technique that you will use here is a U substitution, because that's all you know how to use right now. There's a whole bunch of them, but for right now, the one that works beautifully on this is a U substitution. So what is a good tactic? Something that I should tell you right now is a very good tactic for this problem or any substitution problem. So the tactics for U subs here, the first thing I always suggest is look for the largest expression in your integrand, whose derivative is roughly also in the integrand. Now I say the largest, that's a very important word. Look for the largest expression. And that's mainly because if you under substitute, in other words, if you could have substituted for more, you're going to waste time. So look for the largest expression that you would want U to be. And also try to make that expression something whose derivative is also something like its derivative is also in your integrand. So looking at this guy right here, there's a lot of messiness with this. And I'd really love it if that wasn't a sign of all that mess right there. I would really love it. So rather than doing a simple sub, so my choice is for you here. I could say U is equal to, I could say it's equal to square root of X, actually. I could. But then that would trade that out, right? That would be a U. But what would I do with this? That'd be a bit of a mess. And also, square root of X is not the largest thing I can grab here. I could also let U equal X to the 3/2. If I did that, notice the derivative or the differential of U would be du is equal to 3/2 X to the 1/2 dx. And notice I do have an X to the 1/2 and a dx to steal. That is perfect. However, that's not the largest expression that I could do a U sub for. In fact, the largest expression I could do a U sub for is everything that is the argument of the sign. If you take the risk, it might be worth it to say let U equal 1 plus X to the 3/2 power. If you do that, du is still 3/2 X to the 1/2 dx. Notice X to the 1/2 dx is actually this picture times that picture. So what I'm going to do is I'm going to keep that highlighted expression on the right hand side, and I'll multiply both sides by 2/3 to get that 2/3 du can replace that X to the 1/2 dx. All right, so we have our replacements. Now I'm going to grab this integral and I'm going to say it is equal to the integral of, remember the highlighted root x dx is going to be stolen away for a 2/3 du. And then the only thing we have left is a sine of 1 plus x to the 3 halves. However, 1 plus x to the 3 halves, that's u. Look how clean this integral is now with a simple u substitution. So again, the tactic here was look for the biggest piece that you could substitute in for. Maybe its derivative also is in the integrand. So I took the biggest chunk I could substitute in for, 1 plus x to the 3 halves. Its derivative, roughly, besides the constant, is in the integrand. And I substitute all that stuff in, I get down to here, and I say, oh, the antiderivative of sine is a negative cosine. Don't forget the plus c, because this is an indefinite integral, so always indefinite integrals have the plus c. And once you get to this, you could say, well, did we start in the world of u? No, we did not. So you're going to have to resubstitute in the end. Always with indefinite integrals, if you use the substitution method, you're going to have to resubstitute in the end. And this will equal a negative 2/3 cosine of 1 plus x to the 3 halves, then plus c. Again, u was 1 plus x to the 3 halves. That is the integral of the square root of x sine of 1 plus x to the 3 halves dx. Or in other words, the antiderivative of that integrand. You could always check your work by taking the derivative of this. It will, I promise, I'm not going to do it, but it will turn into the original integrand. That's a great way to check your work on an exam. Now, this seemingly innocent integral always throws students off the first day of Calc 2. I walk in the door and I say, integrate the cotangent or integrate the tangent. They're basically the same style of problem. And people just go, they kind of stare at it for a while. Some people hem-haw. Some people say it's the negative cosecant squared, but that's not the antiderivative. That's the derivative. So not the same thing, right? So then my students start thinking about, okay, well, what would I take the derivative of to arrive at that integrand? Well, I don't know. I don't know what I'd take the derivative of to arrive at cotangent. So then they start thinking, look for the largest expression whose derivative is roughly in the integrand. What? I can't, there's only one expression in this integrand. There's nothing I can do. Or is there something you can do? If that tactic for looking for the largest expression whose derivative is roughly in the integrand doesn't work, you might need to just rewrite the integrand using algebra or trig. So there, I've added that to our tactics here. Rewrite the integrand using algebra or trig identities. This cotangent is the same thing as cosine over sine. And now we have a little bit of hope because I see a couple of functions in this integrand whose derivatives are also in this integrand. For example, the cosine, its derivative is actually in this integrand. And the sine, its derivative is in this integrand. It's not the exact derivatives, by the way. So the derivative of the cosine is actually a negative sign, but I don't really care about constants or negatives. I just care about is the function part of the derivative within this. But you have to make a decision at this point. Which is going to be the good substitution? Because one is going to work, and I promise the other will not. Let's start with the one that will not work. I'm going to write it in red. Not that it's bad to try. It's always good to try, but it's just the wrong choice. And we'll see why. If you let u equal the cosine, well then, du will steal away a negative sine of x dx. The question here is, do you have a dx times, let me point that out and just say this is times here, not divided by, but times. Do you have a sine of x times dx in your integrand? And the answer is no, you don't. So that might be a bad substitution because I don't have a dx and a times the sine of x to steal. In fact, I'll write that down. So in this case, we will quickly try the other method. And by the way, this is what you're going to do throughout Calc 2. You'll start opening one door and realize, that might not be a good choice. Let me try something else. You'll always pivot with tactics. That's something you have to get used to. You have to be okay with just quickly pivoting after trying something. You have to know when it's a good time to walk away, right? So if you let u equal sine of x, well then the derivative, or the differential, that will imply that du is equal to the cosine of x dx. In other words, I'm looking to steal a cosine of x times a dx. Do I have a cosine of x times a dx? Yeah, I sure do. It's right there. So that highlighted picture in my integrand there will be replaced with a du. It's a simple substitution. I don't mean simple like, oh, everybody should have seen it, but I mean like it's a straight substitution. Cosine of x dx gets substituted immediately for a du. So this is a good sub. I have the integral of 1 over the sine, which we're calling u, du. And we know the antiderivative of 1 over u is the natural log of the absolute value. Do not forget that absolute value sign of u plus c. And then remember, you need to resubstitute in the end. So this will be the natural log of the absolute value of the sine of x. And then plus c. That's it. That's the antiderivative of the cotangent, the natural log of the absolute value of the sine. You could double check by taking the integral, but I promise, or taking the derivative, but I promise that is actually the antiderivative. So let's say you're working on an exam and you're faced with this indefinite integral and you stare at it, intimidated. You don't know what to do, right? You look at that and you say, I don't know the antiderivative of the integrand. I don't know what I would take the derivative of to arrive at that integrand, right? So you're thinking about this advice right here. What would you take the derivative of to arrive at the integrand? And you go, I don't know. Then you say, well, maybe I could do a substitution. And actually here you totally can do a substitution, like a straightaway substitution. But there's something about this that most people will be attracted to doing. And there's nothing wrong with it, but I'm just telling you, it's something that most people would be attracted to do. Most people would say, well, let me use a trig identity. Now, I'm not saying this is wrong, but this is a great example to showcase that going down a path, one path might be longer than another. So let's suppose that we use the trig identity here. Let's say that we use the fact that sine of 2x is 2 sine of x times the cosine of x. Let's just pretend that you did that. And the denominator is still 3 plus cosine squared of x. And then you have this dx. And you look at this and you say, okay, I'm going to do a substitution. Now, my advice with substitution is try to let u equal the largest expression whose derivative might also be there. Well, if you look through all of this, some people will say, I'm going to let u equal the cosine. If you let u equal the cosine, I'll write it in red. Not that it's bad, but it's not the way I'm going to go. But if you let u equal the cosine of x, you'll see that du will steal away a negative. The negative doesn't actually matter, but the negative sine of x dx. So the question is, do we have a sine of x dx to steal? And the answer is totally. I have a sine of x dx right there. All the other stuff becomes u, right? But when you do this u substitution, you will get stuck. You'll get the integral 2, remember, sine of x dx is going to be traded out for a du and a negative, because I'm going to move that negative to the other side, okay? So negative du gets traded out for a sine of x dx. Okay. So the highlighted stuff here is gone. Everything that says cosine of x, I can call that u. And you stare at that. And actually you can technically continue forward, but this would require a double substitution because you did a small substitution to begin with. Notice how small this substitution is. It's just u equals a regular old cosine. Let's just see what you'd have to do to finish this problem out. If you find that you're doing more than 1 or 2 substitutions, you're doing too much, okay? So in this case, let's say that you were handed this and they said integrate. And you go, man, I don't know the antiderivative of that. Can you do a substitution? Yeah, you certainly can. You can let v, because u is now being used, you can let v be this entire denominator. If you let v be that denominator, the derivative of that denominator is 2u, which is in the numerator. Again, let me showcase that. If you let v equal 3 plus u squared, let me clean up that square, you'll see that dv is equal to 2u, that's the derivative of this picture right here, times du. The question is, do I have a 2u times a du to steal? And the answer is, yep, you sure do. It's, I don't want too many highlighters here, so let me erase this highlighter if I can. There we go. All right, we have a du times a 2u right there. We could totally steal that. So replace that with dv. So this will be a negative integral. The 2u du gets replaced by a dv, and we'll just have a 1, simply a 1 upstairs. Downstairs we have a 3 plus u squared, but that is called v. And you look at this and you say, I could totally integrate this, and you can. This becomes the negative natural log of the absolute value of v, and then plus c. Did you start in the world of v? No, you didn't. V is 3 plus u squared. Okay, so it's negative. Whoops, I forgot the negative. Sorry about that. Negative natural log absolute value of 3 plus u squared, and then plus c. Did you start this problem in the world of u's? No, you didn't. What is u? It's the cosine of x. So this is going to be the negative natural log absolute value of 3 plus the cosine squared of x, and absolute value plus c. A little side note, by the way, at the end here. 3 plus the cosine squared is always positive, so you don't need the absolute values in the end on this specific problem, so you could write this as the natural log of 3 plus cosine squared of x. Be aware of that. So if you're working in an online homework system and you write absolute values and you get marked wrong, just take a look at what your integrand, or sorry, your argument for your natural log is. If it's always positive, then likely just removing those absolute values will make you correct, even though they are actually the same answer. Now, I told you I'd do this 2 ways. This way required a double substitution, right? You did a small substitution to begin with, and then had to do a secondary substitution, and we had to use 2 different letters, like a U and a V. But another way you could have approached this problem from the get-go, you could have just said, you know what, I'm going to take a flyer on this. I'm going to just take a big bet, and I'm going to bet that I can let u equal 3 plus that cosine squared. There's nothing wrong with trying. If you do that, du should steal away by the chain rule. 2 times the cosine of x. Let me clean that up. Right? We brought down the 2, right? But then, again, by the chain rule, take the derivative of the interior function, the cosine, which will be a negative sine of x. And then you have a dx. And you ask yourself, do I have a 2 cosine of x sine of x dx to steal? And if you say no, it's because you're not thinking in terms of trig identities. That is actually 2 sine of x cosine of x. So we actually do have a dx times 2 sine of x cosine of x to steal away. So I'm going to steal all that stuff away and replace it with a negative. Let me just showcase that I'm going to move the negative to the other side. Replace it with a negative du. If you did that substitution, again, from my first piece of advice, look for the largest expression whose derivative is roughly in the integrand. So if you do that, you have the following integral. So our integral becomes, or equals, negative, because of this negative from the du here, integral of the sine of 2x, which is 2 sine of x cosine of x dx, gets traded out for a du. Again, there was a negative that got thrown out front. We have a 1 over, and that denominator, 3 plus cosine squared, we just called u. And look how quickly we arrived at the negative natural log absolute value of u plus c, where u is 3 plus cosine squared of x. Negative natural log absolute value 3 plus cosine squared of x. And obviously, again, you don't need the absolute values on this one because that's positive. Same answer, right? Just you get to it faster if you would follow my advice. Do the largest substitution that you can. The only thing that you risk is just a few extra moments of being wrong versus possibly being wrong, possibly being right, but taking a long time getting there. So again, just trust me when I say always look for the largest thing you can substitute in for. All right, let's take a look at this guy. Evaluate the integral of secant to the 8th of x times tangent of x dx. This is, again, a really good problem that can be done several ways. So the first thing I'm going to look for is the largest expression whose derivative is roughly in the integrand. Now, if you take a look at this, you have a couple functions there, right? Secant to the 8th and a tangent. Now, let's think about derivatives. What's the derivative of the tangent? Well, the derivative of the tangent, if I let u equal the tangent, it would steal 2 powers of the secant away, right? Because that's secant squared. Derivative of the tangent, secant squared. So that is a viable substitution, possibly. If you let u equal the secant, its derivative will steal away secant tangent, which actually is really nice. So either of those will work. In fact, you could also write this whole thing in terms of sines and cosines. So there are 3 ways to integrate this, and I'll showcase all 3. I'll showcase them from the order that I would probably say not to go from to the best. So the first one, which is one that I think most students would do initially, is they would transform this all into sines and cosines. So the tangent is sine over cosine, and then secant is 1 over cosine, and we have 8 powers of that, so we'll have 9 powers on that cosine in the denominator in the long run. So a lot of students will do this, and then they look and they say, okay, well, what am I going to do my u substitution for? And they've learned by the time they get to this point that, oh, allowing u to equal that denominator, not cosine to the 9th, but just the cosine, would be a good choice. And it is. Absolutely. Let u equal the cosine of x, then du will be the negative sine of x dx. And I'm just already isolating, moving the negative over because I know that my integrand has a dx times the sine of x ready to go. I'm going to trade it out for a negative du. So this will become the negative, I'll pull out front, du, the numerator's gone, and the denominator's cosine to the 9th, which is u to the 9th. This is not a terrible method, it's just probably not the way I would have done it, but this is negative u to the negative 9th du. And now I will add 1 to the power, right? So negative u to the negative 8th, and I'll divide by that new power, plus c. And this will be 1/8 u to the negative 8th plus c. And we then resubstitute in what u is, which is cosine. And I'll park that downstairs as well. So this is just going to be 1/8 cosine to the 8th power of x, and then plus c. That is absolutely the correct answer. It's not that it took us forever to get there, so this is one way we could do it. So number 1, that's the first way that most people would probably go about this. The next 2 ways that I'm going to showcase this are competing ways that you would do this in a Calc 2 course. The first way, again, or I should say the second way since I'm already labeling it that, is to, again, starting with the integral of secant to the 8th of x times the tangent of x, is to say I'm going to let u equal tangent. A lot of students will do that, and that's perfectly fine. U equals tangent of x implies that du is equal to the secant squared of x dx. Now, if you do this substitution, you have to ask yourself, do you have 2 powers of a secant to steal away times a dx? And you do, actually. Let me showcase that. This is secant to the 6th of x, tangent of x, times secant squared of x dx. right? It takes a little bit of rewriting, but you totally do have a secant squared of x dx to steal away. And you would call that du. So let's see what happens with this substitution. You get the integral of secant to the 6th power of x times tangent, which is u, times du. And you stare at this for a moment and you say, I can't do anything with this, because it looks like you can't do anything with this. However, if you remember my advice over here, one of my pieces of advice is to rewrite the integrand using algebra or trig identities. And there is a trig identity that could be used here if you want. You could say that secant to the 6th is the same thing as secant squared to the 3rd. Okay, that's the algebra part of it, I guess. But secant squared is 1 plus tangent squared. So when I tell my students that they have to be awesome with trig before they get to Calc 2, it is no lie. Nobody's going to remind you of these identities as you're working through Calc 2. You just have to remember them off the top of your head in the middle of an exam when nobody's done them for a long time. So it's very important that your trig is super solid. But once you get to this, you realize, wait, u is equal to the tangent of x. So that tangent squared is actually just a u squared. So this is the integral of 1 plus u squared cubed times u du. And this requires a lot of multiplying out because that's a polynomial. So you'd multiply all that stuff out to get a bigger polynomial. You could technically do a u substitution here as well, but I'm going to go ahead and showcase it as multiplying out. If you were to multiply this out, you would get u plus 3u cubed. Sorry, I'm doing it as I'm writing it as I'm computing it. Plus 3u to the 5th, 4th, 5th, plus u to the 6th, 7th du. Okay. And now you can take the antiderivative, right? Each of those, like the antiderivative of u is 1/2 of u squared. The antiderivative of 3u to the 3rd is 3/4 u to the 4th. The antiderivative of 3u to the 5th is 3/6, which is 1/2 u to the 6th. And the antiderivative of u to the 7th is 1/8 u to the 8th. And remember, you have a plus c. And then you substitute in what u is equal to, which is tangent. So this ends up being 1/2 tangent squared of x plus 3/4 tangent to the 4th of x plus 1/2 tangent to the 6th of x. I'm chuckling because I would never want to do it this way. Plus 1/8 tangent to the 8th of x plus c. That is actually the same answer as our simple answer up above, which was 1/8 cosine to the 8th power of x plus c. They're the same answers, just this one at the bottom here requires a lot of compression to get it down to that format. So you can see the difference between those two methods. So the first method, which I say a lot of students kind of do, is actually, in this case, a much better method. But let me showcase one last way to do this. It's going to involve a u substitution, but this time I'm going to let u, instead of be tangent or cosine, I'm going to let you be the secant. So the third way, I'll let u be the secant. Let's write that in. Let u equal the secant of x, which will imply du is going to be the secant of x times the tangent of x, dx. Now the question is, going back to our integral, do we have a secant times a tangent times a dx to steal? And you better say yes, because we totally do. We have a dx, a secant, and we can steal away 1 power of that secant right there. If you did that, you would get, I'll just bring this down here, you would get this equals to the integral. Well, we've stolen away a single power of the secant, so we're left with secant to the 7th. The secant tangent dx gets stolen away for a du. Oh, by the way, u is equal to secant of x. So this is u to the 7th du. Now, if you don't find that to be super nice, then you're wrong. The antiderivative of u to the 7th is 1/8 u to the 8th plus that constant. And u in this case was secant. So this is 1/8 secant to the 8th power of x plus c. Do you see how simple that was compared to the other two? The only reason that you would ever know to do that specific tactic is by working with calculus for a while. And I don't mean for years, I mean working with calculus for quite a few problems. So if you do every problem that you can in whatever section your substitution rule is in your textbook, you will get proficient enough to make these decisions because integration, as I've said before, is completely heuristic. It's more of, as long as you've done enough of it, you will be good at it, but it takes a long time to get there. So it's okay. All these answers are equivalent. So there's nothing wrong with any of these answers. There's nothing wrong with any of these tactics. It's just that you can see the second tactic takes forever. The first tactic, it's okay, but the third tactic is pretty rad. And by the way, you can easily see the third answer and the first answer are identical. And you can't see it, but all those answers are equal to number 2's answer as well. Now this guy right here is a super common style that's handed to a first year calculus student at the end of a course. You have this weird mixture of functions, natural logs and polynomials or rational functions, but this type of substitution is pretty, well, I don't want to say obvious because that seems insulting, but it is somewhat obvious. Look for a function in here whose derivative is also here. If you don't say natural log of x, well, I'm sorry, it's a natural log of x. Okay, so in this case, you could try a bunch of different things. And you may say, wait, you told me in your tactic, let u be the largest expression. So why wouldn't we let u equal natural log to the 4th power? And the reason why I would not do the natural log to the 4th power is because the derivative, if I did that, of u equals natural log to the 4th power of x, its derivative would be an absolute mess. It would keep the natural log, so natural log to the 3rd power of x over x. And that is just not going to work out. While I do have 3 powers of a natural log over x, and a dx to steal, that is absolutely true. I have 3 powers of this to steal over x times dx. Totally have that. The problem is, when I steal all those, I'm left with a 1/4, because this 4 would move over, du, and then I stole 3 powers of that natural log, so I just have a single natural log of x, and unfortunately, u is the 4th power of the natural log of x. I technically could trade it out. I absolutely could. So somebody could say, well, yeah, but you could take the 4th root of both sides. So u to the 1/4 is equal to the natural log of x. And that is absolutely true. You could do that. Totally. But you're kind of at that point making it a bigger problem than it needs to be. I think this problem will work much better if you just let u equal the natural log. If you let u equal the natural log of x, we get that du is equal to 1 over x dx. The question is, do we have a 1 over x dx to steal? And the answer is yes. So we're going to steal that out. Our integral will become the integral of, well, natural log of x is u, and that's to the 4th power, right? Because we have natural log to the 4th, so it's going to be u to the 4th. The 1 over x dx is stolen away and traded out for a du, and look how clean that is. Right? The antiderivative here is 1/5, u to the 5th plus c, and u is the natural log of x. So this is a very nice, fast style of problem, but again, you could totally have done this problem letting u equal the natural log to the 4th power of x, but it takes a lot of manipulation. And again, this is more of a heuristic method, right? The more of these problems you do, the better you'll be at making those decisions to, I'll say, cut corners. All right, this guy right here, I have to keep in the habit of pasting my advice over to the right-hand side. I told you I'd do a lot of examples for this final section because you just need to see all this. This style, do you know the antiderivative? What would you take the derivative of to arrive at this integrand? Your answer should be, I don't know. And that would be a good answer. So what you can do here, there's one of two options. The first option that I'm going to mention is actually probably the safest when you're in a, it is probably the safest when you're first learning integration. So you could let u equal this x plus 6. Now, technically, that's not the largest thing you could let u equal, but I think it's an easier conversation to have to say, let's go ahead and let u equal x plus 6. Well, du is equal to dx. It's just 1 dx. And that's sort of a problem, but actually not too much of a problem. A lot of students don't like this style of substitution, and the reason why is because of the following. This is going to equal the integral. Well, dx gets traded out for a du, and that fourth root of x plus 6 becomes the fourth root of u. But what does this x become? That's what a lot of students dislike. It's like, wait, hold on, what is that x going to be? Well, this kind of forces us to go back to our substitution really quickly, this guy right here, and say, well, if u is equal to x plus 6, then x is equal to u minus 6. That is part of a substitution process. So sometimes you have to do weird things like that in a substitution. And so in this case, we would get this is equal to, instead of an x in the numerator, I'm going to write it as a u minus 6 over u to the 1/4 power, du. And students will still look at this and say, I still don't know the antiderivative. Well, not like that you don't. But if you break this up into u over u to the 1/4 minus 6 over to u to the 1/4, remember algebra before calculus, and if you do some more algebra here, this would be u to the 3/4 minus 6u to the negative 1/4, you now could find the antiderivative. Raise the powers by 1, so this would be u to the 7/4, and multiplied by the new powers, 4/7, the reciprocals that is, minus 6 times u to the add 1 to the power 3/4, and multiply by the reciprocal of that new power, plus the constant c. We know that u, in this case, is equal to x plus 6. And so this would be 4/7 times x plus 6 to the 7/4 minus, what is that, 2 times 4 is 8, x plus 6 to the 3/4, and then plus c. That's one way to do this problem. There is a more advanced way to do this problem. It's actually not too terrible, so I think that I'm still going to introduce it here, although to be honest with you, this normally does not get introduced until about a month into Calc 2. But frankly, if I'm teaching you to look for the largest expression that you can kind of do a substitution for, the largest expression that I could do a substitution for in that integrand is the fourth root of x plus 6. So if I was looking at the integral of x over the fourth root of x plus 6 dx, I could technically say, well, I'm going to let u equal the fourth root of x plus 6. And then you should be very wary of taking a derivative involving radicals because it's just not fun. But you have taken all of Calc 1 at this point, and so you should know how to do implicit differentiation, which means I would prefer to get rid of radicals by raising both sides to the 4th power. I'll have u to the 4th is equal to x plus 6. I just raised both sides of the 4th power to get rid of radicals, and now I'll take the derivative of both sides. The left-hand side becomes 4u cubed times du. On the right-hand side, I'll get 1, that's the derivative of that, times dx. This substitution is actually a very nice substitution because now our integral becomes the following. Integral of, well, the x is still hanging out, but we have to do the same trick. It's u to the 4th minus 6 is equal to x, so I'll just trade that out. U to the 4th minus 6, that's what the x value is. The denominator, fourth root of x plus 6, is u, and dx is going to be traded out for a 4u cubed du. So notice I really simplified this down pretty quickly. The 4 I'm going to move out front. This is equal to 4 integral of u will cancel with that u with 1 power of that u cubed. And then I'll distribute the u squared through, so I get u to the 6th minus 6u squared du. The antiderivative of this would be 1/7 u to the 7th minus 6/3 u to the 3rd. And then you have a plus c out back. And let's see, we're going to go ahead and resubstitute in what u was. U was the fourth root of x plus 6. Remember, fourth root is just the 1/4 power. So I'm going to write it as the 1/4 power of x plus 6. So when you distribute the 4 through, you get 4/7 times x plus 6 to the 7/4 power, because it's x plus 6 to the 1/4 raised to the 7th, so it's 7/4. Minus 2 times 4, or 8, x plus 6 to the 3/4 power, and then plus c. Notice that I get to the same answer as the one on the right hand side. I don't want to say, well, actually it is. It's cleaner. And I find that method to be very useful. You don't have to use it. It's a more advanced method, but you totally can. It doesn't take any other special type of mathematics to do it. You could totally do it today. Now this guy right here, this is a very special case. The integral, indefinite integral, of 8x over x to the 4th plus 1. This is very close to a derivative that we know. Specifically, this sort of looks like, it's not exactly, but it sort of looks like 1 over x squared plus 1, which is the derivative of the tangent inverse. But unfortunately, it's not a 1 over x squared plus 1. And so this is another tactic that I'm going to mention in here, that you often do look for patterns that mimic derivatives. So as I've written here, in some cases, looking for patterns in the integrand that mimic common derivatives is helpful. You'll have to force the derivative with creative substitutions at times. And in this case, the pattern I'm looking at right now, even though that 8x is in the numerator, the pattern that I'm looking at looks like a 1 over x squared plus 1. So I'd really love it to be that. Well, if I want it to be that, I'm going to make a substitution to force that to be a square. And the substitution I'm going to make here is I'm going to let u equal x squared. It's a very, very tricky substitution, but it does help out, because if I let u equal x squared, this will be u squared plus 1 in the denominator. Well, let's see what happens in the numerator. Du will be 2x dx. In other words, I get to steal away 2 times x dx out of that numerator and trade it out for a du. And notice I can totally do that, because this is 4 times 2x dx over 1. I'm going to write it as x to the 4th plus 1. I just have a habit of writing it 1 plus x to the 4th. So that 2x dx in the numerator, I'll trade that out. That's 4 integral du over. And then downstairs, x squared is going to be called u. So x to the 4th is going to be called u squared. Let me clean that up. So this is a u squared plus 1 downstairs. Now the antiderivative of 1 over u squared plus 1 is a tangent inverse of u, one of the most important antiderivatives that you can learn. So 4 times the tangent inverse of u, and then plus some constant c, because it was an indefinite integral. Of course, we did not start with u's, so we'll have to trade that back out. That is 4 tangent inverse of x squared, and then plus c. So we've added something to our list of tactics, looking for patterns that look like common derivatives. Very, very helpful. Now this one I just put in here because I absolutely love this problem. I would recommend you try this problem by pausing the video and just try it yourself. But I am going to just jump right in to the deep waters here and do it. So pause, try to figure this out, but here I go. The first tactic is the best tactic. Look for the largest expression that you can substitute in. Even if you don't know if its derivative is there, just try it. The largest expression that I see is that denominator, 1 plus e to the x. If you do that substitution, if you let u equal 1 plus e raised to the x power, then du is equal to the derivative of 1, well, that's 0. The derivative of e to a power is, well, e to the power. But by the chain rule, you have to take the derivative of that power. What's the derivative of e to the x? It's e to the x. And don't forget, you have a dx there. So the chain rule does come into play quite a bit in Calc 2. You have to be aware of that. The question is, do we have a dx times e to the x times e to the x to steal? And the answer is yep, we sure do. Right there. So this integral actually is written as du, because that steals away the e to the x times e to the x dx, divided by, well, that 1 plus e to the x is what we let u equal. Look how clean that is. And now the antiderivative of 1 over u is the natural log absolute value of u plus a constant c. But u is 1 plus, so I'll write this in here, natural log absolute value of 1 plus e raised to the x. A little side note, 1 plus e to the x is already positive, so you don't actually need the absolute values there. So you can just trade this out like that. And there you go. Now, there are a lot of other ways to do this problem. You could have started by saying, well, I'm going to let u equal e to the x. But if you did that, your derivative would only steal out 1 e to the x, so you'd have e to the u over 1 plus e to the u. And then you'd have to do another substitution. And this problem, I've seen it done by some students using 3 substitutions. Don't do that. If you have to do 3 substitutions, you should have gone back to the beginning and just done 1 major substitution. Look how simple that sub is, and it really simplifies this problem down. So be very aware of that. We are now into the definite integrals, and I just round out the course with this. So the antiderivative here, you do not know what you would take the derivative of to arrive at that, but look for patterns. Look for things that you would take functions in here whose derivatives are also in here. Well, isn't the derivative of the sine inverse here? Here's the sine inverse, and 1 over the square root of 1 minus x squared is its derivative. So I am going to let u equal the sine inverse. I'll just do that right here. Let u equal the sine inverse of x, which will imply du will steal away a 1 over square root of 1 minus x squared dx, which is exactly what we have right here. So this integral, this definite integral, will equal the integral, let's see, we're letting u equal the sine inverse. Everything else gets stolen away and gets replaced by du. Now we have to replace those limits because those limits are x equals 0 to x equals 1/2. So let's go over here and ask ourselves, what is, so if x equals 0, then u is equal to the sine inverse of 0. What is the sine inverse of 0? You should know that. You've taken trig. It's 0. So this will be u equals 0 because when x is 0, u is 0. If x is equal to 1/2, then u is equal to the sine inverse of 1/2. What is the sine inverse of 1/2? You should know it's pi over 6. So that'll be u equals pi over 6. Now that we've transformed completely into a totally different environment, all u's, now we can complete this problem without transforming back. Definite integrals, you do not have to transform back as long as you've properly transformed completely into the world of u. So this will be u squared over 2 evaluated from u equals 0 to u equals pi over 6, and substituting in pi over 6, you get pi over 6 squared over 2 minus substituting in the lower limit, u squared or 0 squared over 2, you get pi squared over, let's see, 36 times 2, 72. That is the area underneath that curve from 0 to 1/2.
All right, here's yet another definite integral. This time we have parameters within this definite integral. This one goes from 0 to some unknown value a. That a is just a constant. You can kind of just think of it as a 5 or a 25 or something like that. It doesn't really matter. The one thing you need to know here is a has to be greater than 0. Mainly so that we can find the area underneath this curve from 0 to some more positive number, right? That's why we want a to be greater than 0. So when you look at this, if you can't see it, you really do not have an antiderivative here that you know of. So we'll go ahead and then assume that we must use substitution. Right? I don't know what I would take the derivative of to arrive at that. So now, following our advice or tactic here, we're going to look for the largest expression whose derivative is roughly in the integrand. Now, in reality, there are a couple really good choices here. And if you haven't sensed it, this is the theme with integration, is that when you're using a substitution rule, you have honestly usually 1, 2, 3, 4 choices, and each of them has its advantages and disadvantages. Well, there's probably an optimal one that has no disadvantages, honestly. So in this case, there's a couple choices for substitution that you could use, and I'll showcase both of them. The first one that I'm going to use is really the one that I think most Calc 2 or Calc 1 students would use, and that is to substitute for x squared plus a squared. Remember, a is just a constant, and the reason why you'd want to do that substitution is because the derivative of x squared is roughly x. You know that derivative, actually I should say the derivative of x squared plus a squared is roughly x. It's actually 2x, but again, when we're talking about is the derivative within this integrand, we mean we don't really care about the constant multiples. We just care about is the actual variable derivative within this integrand. So in this case, a good substitution would be x squared plus a squared. Let's go ahead and see that. Let u equal x squared plus a squared. This would imply this in blue here. What I'm doing is I'm going to transform everything into the world of u. So I have transformed this into the world of u. Now I want to know what dx is in terms of u's. Well, that requires us to take the differential of u. Du is equal to the derivative of this right hand side. Remember, a is just a constant, so it's just going to be 2x. And then times the differential of the variable on the right hand side, dx. And the question is, do we have a dx times an x within our integrand? And we do. Dx times an x right there. So I'll go ahead and isolate that. And I'll divide both sides by 2. So 1/2 du is equal to an x dx. And now I can make that replacement. So not only is the x squared plus a squared going to be written in terms of u, but also the x dx can be written in terms of u as well. Now we have to worry about the limits of integration. And yes, I understand that there are going to be people who are watching this video who have an instructor that might say, oh, don't worry about changing those limits of integration. But I'm telling you, if you don't, you are inevitably going to make the mistake of not switching back to the world of x when you're done. So what's nice about switching out your limits of integration right now is that when you're finished with your integral, you don't have anything else to do. And so I'll show you what I mean at the end of this. If you do not know what I mean, I'll show you at the end what some instructors allow. All right, so when, I'll write it this way, when x is equal to 0, u is equal to, right? We're going from x equals 0 here, so let's find out what u, our lower limit for u, will be. Well, if you let x equals 0 in this equation that relates u to x, u will equal 0 plus a squared. So u will equal a squared. When x is equal to a, that's the upper limit, u is equal to a squared plus a squared, which is 2a squared. And now we have completely transformed that integral into the world of u's. And with definite integrals, if you are doing that properly, just like what I've done there, then you will never have to transform back into the world of x. You will be completely done once you integrate, basically. So we go from u equals a squared to u equals 2a squared of, let's see, x dx gets stolen away and traded out for a 1/2 du. We have the square root of x squared plus a squared, but x squared plus a squared we called u. So we have the square root of u, or in other words, u to the 1/2 power. Notice how nice that integral is now. We just go ahead and raise the power of u by 1, so it becomes the 3/2 power, and multiply the front end by the reciprocal, 2/3. And we are going to evaluate this from u equals a squared to u equals 2a squared. And you know the 2's cancel there, so you get 1/3. I would probably do it like this. Just put a bracket here so that I can keep the constant outside. I can distribute that constant through in the end, but I at least want to write my upper limit, or my function evaluated the upper limit minus my function evaluated the lower limit. I want to write that within that grouping symbol first. So plugging in 2a squared, I'll get 2a squared raised to the 3/2 power minus, and then I'll plug in the lower limit, a squared raised to the 3/2 power. All right, let's go ahead and see what that is after some simplifications. So that's going to be 2 to the 3/2 power. A squared to the 3/2 power is a cubed. Minus, again, a squared to the 3/2 power is a cubed. And let's see, I guess I could just factor out the a cubed. There's really not much else that I see that would make this work. So I'm just going to leave it like this. There we go. So that is the final answer. That's the area underneath that curve from 0 to a. Nice, right? Now, as a modification of this, I'm going to ask an extension here, an extended question. But before I do, I promised that I would show you what I was talking about when I said some instructors allow students to not change limits. So let me go ahead off to the side. Now, this is a very dangerous thing because it leads to a lot of mistakes, but our original integral went from x equals 0 to x equals a, and we had x times the square root of x squared plus a squared dx. Now, all of our substitutions are going to be identical, so there's no extra work that I have to do here. I would have had this almost all of the same setup, with the exception that when I integrate this, if I choose to not change the limits, then I'm integrating 1/2 u to the 1/2 du. And I have mentioned previously, integrating this is illegal because you need all of the variables to be the same. And right now they're not, right? You are integrating with respect to u to the 1/2, but from x equals 0 to x equals a. And the problem is not technically that, because you could still kind of get away with integrating this, but people will often not write x equals 0 to x equals a. And that, if they don't change limits, that leads them to believe that they're integrating with respect to u. So this is what some teachers allow, which again, I do not. But they'll allow students to do this. Oh, that's 1/2 u to the 3/2 times 2/3, and then evaluated from. Now, let me just show you right now. And it's not shorter work, by the way. It just looks like shorter work just because I've already done all the pre-work off to the left. But notice that we're pretty much at the same point. 1/2 times 2/3 times u to the 3/2. In red, 1/2 times 2/3 times u to the 3/2. However, people will write this, oh, from 0 to a. Note, if you were just to plug in a and then 0, right? So u to the 3/2 evaluated at a and u to the 3/2 evaluated at 0, you'd be totally wrong, because those zeros and those a's, or that 0 and that a, are in terms of x, not in terms of u. And so then, if a teacher allows this, they tell their students, by the way, if you're going to do this, you have to remember that these are actually x equals. And so you have to transform this back into the world of x. So you have to go all the way over here and say, what's u equal to? Oh, it's equal to x squared plus a squared. Okay, so this is now 1/3 times x squared plus a squared to the 3/2, evaluated from 0 to a. And then they plug in 0 and a, right? So it's going to be 1/3 times, if you plug in a, you'll get a squared plus a squared, or 2a squared, to the 3/2 power. And minus, if you plugged in 0, you'd get 0 plus a squared, or in other words, a squared, to the 3/2 power. And this is actually the same destination. We're actually at the same step here. And so everything else will be the same. But again, I tell you not to do it this way because two things. One, this integral you actually cannot do because the definite integral is not defined to go from x equals 0 to x equals a of something in terms of u with respect to u. The definite integral is not defined to work that way. But you technically can get away with it a little bit. However, you often, I've taught for years, so I know this is the case. People often forget that this is in terms of x and this is in terms of x as well. And so they just plug that in. And so here's my warning to my students, if you're in one of my classes, is that if you choose to not change your limits because you say, well, I get all the right answers because I always remember to change this u into the world of x at the end, you know, I'm not going to yell at you. I'm not going to dock you points. But the moment that you forget to change, you'll get 0 points because I've warned you. You should change your limits of integration. And there'll be a moment, I guarantee it, when you forget to do it. And I'm going to guarantee it, it'll happen on an exam. So that's just my warning to my students. And I'd like to just make that warning to other students. Don't make that mistake. All right. One last thing I want to say here about this example, and I know this video is long, but it is the last topic in all of differential calculus, is that I could change this question very slightly to be the following. Integrate from negative a to a, x times the square root of x squared plus a squared dx. Now, if you go to tackle this problem and you say, if you see this problem, let's say this is on your exams or something like that, and your professor says, hey, I'd like you to integrate this from negative a to a. You should always check for symmetry. You should ask yourself, is that function odd or even? And the reason why is because you don't have to speed through and do all the computations. If I go from negative a to a, well, let's let f of x here equal x times the square root of x squared plus a squared. Then f of negative x is equal to negative x times the square root of a negative x being squared plus a squared, which is negative x times the square root of x squared plus a squared, which is actually the opposite of the original function. So this right here is odd. It's an odd function. And you're integrating that odd function, which is symmetric about the origin. By the way, this is not what the function looks like, but I'm just giving you what a standard odd function might look like. You're integrating that function, or finding the area between that function and the x-axis from x equals negative a to positive a. In other words, a symmetric interval. So this area and this area should be the exact same. And if they are, one is positive, one is negative, that'll be 0. So this is just a heads up that if you see a symmetric interval, take advantage of it. Take a look if it's odd or even. By the way, if this was even, just pretend for a second that this is x to the 4th, here. If this was an even function, then you would just say, I'll just integrate it from 0 to a and take twice it. If you don't understand why, it's because an even function has the property that it's symmetric about the y-axis. And so if I'm integrating from negative a to a, that area there is the same as that area there. So really, instead of integrating from negative a to a, I could say, nope, I'm going to integrate from 0 to a and just double it up. So just to let you know, that is, those are good tactics to pay attention to in your integrations. It just speeds things up immensely. And the final example in all of differential calculus, you have arrived. It's a very simple question. Why can't we evaluate the integral from negative 5 to 5, 4t divided by 2 minus 8t squared dt? It's an innocent looking integral, and actually, if you were to take a look at it and write it down, like in a bigger format, because I dislike how that's formatted there, so I'm just going to rewrite it down below. If you take a look at this, a u substitution will actually help out significantly if you could integrate this. But there's a hidden issue, something that you have to be aware of when you're integrating or when you're working with definite integrals. If it's an indefinite integral, then there's no issue. Just find the antiderivative. But a definite integral, yep, you'll have some issues here. And the reason why is domain. Domain issues you have to watch out for. Notice that that denominator is 2 minus 8t squared. You do not want that denominator to be 0. Well, that means you do not want t squared to equal 1/4, which means you do not want t to equal plus or minus 1/2. And unfortunately, this interval contains a negative 1/2 and a positive 1/2, this interval right here. So you have some discontinuities in here, and that's an issue. You have infinite discontinuities, really. That's the issue. Not that you have discontinuities, but that you have infinite discontinuities. So why can't you evaluate this? The integrand has infinite discontinuities at plus and minus 1/2, which is part of the interval you're integrating across. Okay, so it has been my pleasure to have offered these videos to you this entire time. I hope that you have learned at least one thing, if not a few things, from my video series. If not, I apologize. If so, I am honored that you paid attention. And I hope that you have immense amounts of success in life, in academics, and that includes the most important thing, happiness.
It's What's the system of equations? We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.